Hello guys, we want to start lecture 35. In this lecture, we want to talk about solution of heat equation. So we have one heat equation. So the heat equation, we talked about it in the last lectures, and we said if we don't consider the effect of surrounding medium on the rod, so we assume that F is equal to 0, and general form of heat equation is k times second derivative of u with respect to x is equal to derivative of u with respect to t. We know that the length of the rod is L. As a result, x is defined between 0 and L, and so t is greater than 0. We have boundary condition. So boundary conditions identify condition of the system in the boundaries. So we have temperature at 0 and at x equal to 0 is equal to 0. And we know that temperature at the end of the rod, which is u of L and t, is equal to 0. So we have these two boundary conditions. And we have initial conditions, which identifies condition of the system at t equal to 0. We know that u of x and 0 is equal to x. So in fact, we have a boundary value problem. This one is a boundary value problem because we have partial differential equations subject of boundary conditions and initial conditions. In order to solve this equation or this boundary value problem, in fact, we want to find u of x and t. So we want to find u of x and t, which is temperature function. And this function should satisfy partial differential equation given here, and it should satisfy boundary conditions and initial conditions. In this chapter, if you want to solve a partial differential equation, the only technique that we use is separation of variable. So we assume that u of x and t is equal to x of x times t of t. So now we have to find, the solution of this problem is a little bit long, but the procedure is exactly the same for all the problems. So as a result, if you follow this solution, you're going to be fine for all the problems. So now we have to find second derivative of u with respect to x. So second derivative of u with respect to x, it's equal to x double prime times t. And derivative of u with respect to t, it's equal to x times t prime. If I plug it in the partial differential equation, we will have k times second derivative of u with respect to x. So it's equal to, we found that it's equal to x double prime times t. It's equal to derivative of u with respect to t, it's x times t prime. As a result, x double prime divided by x, it's equal to t prime divided by kt. So we have two functions of different variables. The left one is function of x, the right one is function of t. If they want to be equal, they have to be constant. We talked about it in the past lectures, and they should be equal to minus lambda. So we have x double prime over x is equal to lambda minus lambda. As a result, we have x double prime plus lambda x, it's equal to 0. And we have t prime divided by kt is equal to minus lambda. So it means that t prime plus lambda t, it's equal to 0. So instead of solving partial differential equation, now we have two ordinary differential equation and we have to solve it. It's the first step in solving these type of boundary value problems. The second step, we have to go through the boundary condition and we have to find boundary condition for ordinary differential equation. The first boundary condition that we have here, so it says that u of 0 and t is equal to 0 is the first boundary condition. So boundary condition The first one said that u of 0 and t is equal to 0. U of 0 and t is equal to 0, so it means that x of 0 times t of t is equal to 0, because here we defined u of x and t as x of x times t of t. So now x is here is equal to 0. So if we have these guys, so it means that either x of 0 is equal to 0 or t of t is equal to 0. T of t cannot be equal to 0, because if it's equal to 0, so here you can see the equation of temperature. So it means that the temperature function is equal to 0, so but it's not. As a result, this one is not valid. So it means that x of 0 should be equal to 0. The other boundary condition that we had, so it said that u of L and t is equal to 0. So we have u of L and t is equal to 0. As a result, x of L times t of t should be equal to 0. It means that either x of L is equal to 0 or t of t is equal to 0. Again, t of t cannot be equal to 0. As a result, x of L should be equal to 0. So now for this ordinary differential equation here, so we have x double prime plus lambda x equal to 0. We have two boundary conditions. We know that x at 0 is equal to 0 and x at L is equal to 0 as well. Now we have to solve this ordinary differential equation. In order to solve this ordinary differential equation, like last lecture, we have to consider three different cases for lambda. So in the first case, we assume that lambda is equal to 0. If lambda is equal to 0, it means that x double prime plus lambda x is equal to 0. So lambda is equal to 0. So it means that x double prime is equal to 0. As a result, x of x prime is equal to a constant. I call it b1. And x of x is a linear function. So it's b1 x plus b2. b1 and b2, they are constant. So if lambda is equal to 0, we have x of x equal to b1x plus b2. Now I have to apply boundary condition. So the first boundary condition says that x at 0 should be equal to 0. If I plug 0 here in this equation, so we have b2 should be equal to 0. The second boundary condition says that x at L should be equal to 0. If I plug L in this equation, so we have b1 times L should be equal to 0, because b2 is already equal to 0 here. So b1 times L is equal to 0. So it means that b1 should be equal to 0. So in fact, if we assume that lambda is equal to 0, both b1 and b2 are equal to 0, it means that x of x is equal to 0. But it cannot. Why? Because at the beginning we defined u of x and t as x of x times t of t. If x of x is equal to 0, so it means that the temperature function is equal to 0, and it's not a solution. As a result, lambda cannot be equal to 0. We go through the next case. In the next case, we assume that lambda is a negative number. So we assume that lambda is equal to minus alpha squared. If lambda is equal to minus alpha squared, here we have the equation. So we have x double prime. So we had plus lambda x. Lambda is minus alpha squared. So it's going to be minus alpha squared times x. It's equal to 0. Solution of this ordinary differential equation, you have it in the formula sheet. It's equal to x of x. So we already used b1 and b2. So I use b3 as a constant. b3 cosine hyperbolic alpha x plus b4 sine hyperbolic alpha x. Now we have to apply upper limit and lower limit. So we have x of 0 it's equal to 0. X of 0 it's equal to cosine hyperbolic of 0 it's 1. So we have b3 times 1, and sine hyperbolic it's equal to 0. So it means that b3 should be equal to 0. Here I just say a note about sine hyperbolic and cosine hyperbolic. So it's just a note. So cosine hyperbolic of alpha x it's equal to e to the power of alpha x plus e to the power of minus alpha x divided by 2, and sine hyperbolic of alpha x it's equal to e to the power of alpha x minus e to the power of minus alpha x divided by 2. It's just definition of cosine hyperbolic and sine hyperbolic. So you can see that cosine hyperbolic at 0 is equal to 1, but sine hyperbolic at 0 is equal to 0. So, and the other thing that you have to know, so sine hyperbolic and cosine hyperbolic, they are not periodic functions. So they are exponential functions. The other boundary condition that we have, so it's x at L should be equal to 0. So it means that x of L, if we find it using this equation, so we already know that b3 is equal to 0. So we have b4 sine hyperbolic alpha L is equal to 0. If you look at the sine hyperbolic equation here, sine hyperbolic is 0 only at x equal to 0. If x is not equal to 0, so sine hyperbolic cannot be equal to 0. As a result, in this case, b4 should be equal to 0. So again, we can see that b3 is equal to 0, b4 is equal to 0. As a result, x of x is equal to 0. Again, we ended up with x function equal to 0. So it means that temperature function is equal to 0. As a result, this for lambda equal to minus alpha squared. So again, it's not solution of this problem. So we have to consider the third case. In the third case, we assume that lambda is a positive number. So in the third case, we assume that lambda is a positive number like alpha squared. So we have the equation, it's x double prime plus alpha x is equal to 0. And we said lambda is equal to positive number, so it's x squared plus alpha squared x is equal to 0. As a result, x of x it's equal to, we use b3, b4, so here we use b5 cosine alpha x plus b6 sine alpha x. Now we have to apply the boundary conditions. So x of 0 is equal to 0. So x of 0 based on the equation that we found is b5 cosine 0 is b5 plus b6 sine 0 is 0. So in fact b5 is equal to 0. The other boundary condition, so we have x of L is equal to 0. So it means that if we find x of L, so it's equal to b5 already equal to 0. We have b6 sine alpha L is equal to 0. If b6 sine alpha L is equal to 0, it means that b6 is equal to 0 or sine alpha L is equal to 0. If b6 is equal to 0, we already have b5 equal to 0 as well. As a result, x of x is equal to 0. So we have a temperature function which is equal to 0. It's not the solution of the problem. So we can say that b6 cannot be equal to 0. But what about sine alpha L? Sine alpha L can be equal to 0 if alpha L is equal to n, which is positive integer number, times pi. Because you know that sine pi is equal to 0, sine 2 pi 0, sine 3 pi equal to 0, and so on. As a result, if alpha times L is equal to n times pi, so in this case, sine alpha L is equal to 0. So it means that alpha is equal to n times pi divided by L. And x of x, now it's equal to b5 is equal to 0, but we have b6. So it's b6 sine alpha x. Alpha we found it, it's equal to n times pi divided by L times x. So we could find x of x when lambda is a positive number. So we know that lambda is equal to alpha squared here, and alpha is equal to n pi over L. So we have n squared, pi squared, L squared. So here we have lambda equal to n squared, pi squared over L squared. So here I call it lambda n because we have different lambdas for different values of n. N can be equal to 1, 2, 3, 4, and so on. It's a positive integer number. In this case, we call lambda n as eigenvalues of the system. And we call x of x that we found in this equation, so as eigenfunctions of the system. Functions of the system. So we could find x of x. Now we have to find t. So at the beginning we said we have one ordinary differential equation for t. So t prime, what was the equation? Let's see here. So we had t here. T prime plus lambda t should be equal to 0. So we have t prime plus lambda t should be equal to 0. So it means that if you solve this ordinary differential equation, so you have the solution in the formula sheet. So we have we use b6, so we have b7 e to the power of minus lambda t, or it's equal to b7 e to the power of minus lambda. We know that it's here, it's n squared pi squared over L squared. So we have n squared pi squared divided by L squared times t. And we said u of x and t, it's equal to x and x of x, t of t. X of x, we found it, it's equal to b6 sine n pi over Lx. And t of t we found is equal to b7 e to the power of minus n squared pi squared divided by L squared times t. I think I made a mistake here. Yes. Here I made a mistake. When we have t prime over kt is equal to minus lambda, so here we have t prime plus k lambda t is equal to 0. And here we have t prime plus k lambda t is equal to 0. Here we have minus k lambda, and here we have minus k n squared pi squared over L squared times t is equal to 0. And we have x of x times t of t, so we have k minus k n squared times pi squared over L squared times t. So it's u of x and t, and so you can see that for n can be equal to 1, 2, 3, and so on. So in fact, for any values of n, u of x and t is a solution of this problem, and it can satisfy partial differential equation or heat equation and boundary condition. As a result, we can say we have u n of x and t, because for any value of n, it's a solution. And so I assume that b6 times b7, so is a constant. I call it an, b6 times b7, why an? Because for any value of n, we have one constant, so that's why I call it an. So we have sine n pi divided by L times x, e to the power of minus k n squared pi squared divided by L squared times t. So we found un of x and t. So the un of x and t, I already said it satisfies a partial differential equation or heat equation and boundary conditions. But we have to see if it can satisfy initial condition or not. So what's the initial condition? So the problem says that the initial condition is that u of x and 0 should be equal to x. So let's find u of x and 0 for our solution. So initial condition says that u of x and 0 should be equal to x. So in our solution, we have un of x and t is equal to an sine n pi over lx times e to the power of minus k n squared pi squared over L squared times t. Let's find un of x and 0. It's equal to an times sine n pi over lx times e to the power of 0. E to the power of 0 is equal to 1. We have to see if this function is equal to initial condition or equal to x or not. For sure it's not, because an is a constant, then we have a sine n pi over lx. It's a harmonic function, it's not equal to x, which is a ramp function. As a result, our solution cannot satisfy initial condition. It just satisfies heat equation or partial differential equation and boundary condition. So we say that un of x and t satisfies heat equation or partial differential equation and boundary conditions, but does not satisfy initial condition. What we have to do if it does not satisfy initial condition? So here we see that un of x and t is a solution for the problem that satisfies partial differential equation and boundary condition. Based on superposition principle, if un of x and t satisfies PDE and boundary condition, summation, linear combination of un should satisfy as well. So based on superposition principle, u of x and t, which is equal to summation of un of x and t, n from 1 to infinity should satisfy partial differential equation and boundary condition. Because in the last lecture we said if u1, u2, u3 up to uk, they are all solution of a problem. Linear combination of them is a solution of the problem as well. As a result, u of x and t, which is summation of un, should satisfy partial differential equation and boundary condition. So in fact, u of x and t is equal to summation of n from 1 to infinity. Un of x and t we said is equal to an sine n pi over lx e to the power of minus k n squared pi squared divided by l squared times t. Initial condition says that u of x and 0 should be equal to x. Based on the solution that we found here, u of x and 0 it's equal to summation of n from 1 to infinity an sine n pi over lx. And e to the power of 0 is equal to 1. So based on the initial condition, so this guy should be equal to x. In fact, if we can find an such that summation of an sine n pi over lx n from 1 to infinity is equal to x, so we could find solution of the problem. If you look at this term, so you can see that this guy is half range sine series. And for half range sine series, we had an, it's equal to 2 over L, integral from 0 to L, fx sine n pi over Lx dx. So here in this case, fx is equal to x. As a result, an is equal to 2 over L, the integral from 0 to L, x sine n pi over Lx dx. If you just find this integral, you can see that it's equal to minus 2L cosine n pi divided by n times pi. So now we could find solution of this problem. So in fact, u of x and t it's equal to summation of n from 1 to infinity. So we had u of x and t, it was summation of an sine n pi over lx times e to the power of minus k n squared pi squared over l squared times t. Here we found an, so I just plug it here. So an is minus 2L cosine n pi divided by n pi times sine n pi over lx times e to the power of minus k n squared pi squared divided by l squared times t. So we could find solution of this heat equation, and it can satisfy heat equation, boundary condition, and initial conditions.